Hello, everyone. Welcome to our Wednesday seminar. And today we are very happy to have David Cyncynates from Stanford, and he's going to tell us about his interesting work about axion dark matter. David.
All right, thank you for the introduction and for the invitation. Today I'll be telling you about some recent work with my collaborators, Tudor, Olivia, and Jed over at Stanford, and a little bit about some forthcoming work with Zach Weiner over at the University of Washington. So to get us started, axions are well-motivated extensions of the standard model. You have the QCD axion, which is hypothesized to resolve the strong CP problem. And you have string axions, which arise from the complicated topology of the extra dimensions of string theory. Now, in both cases, the axion is a naturally light particle. This is because they acquire their potential purely through non-perturbative effects. In the case of the QCD axion, it acquires its potential through strong instantons, which are down at the QCD scale, and string axions acquire their potentials through stringy instantons. In both cases, the instanton potential is periodic. This is because the axion is a periodic field, corresponds to winding. And the scale out front is what we call the instanton scale. This is what is generated non-perturbatively, and thus naturally lives at whatever scale it ends up at. On the other hand, inside the cosine here, we have the axion field phi divided by f. F is known as the decay constant, and it suppresses the axion's self-interactions and the axion's interactions with the standard model. And so it is important that f naturally lives up in the UV, making the axion a weakly coupled particle, and thus a good candidate for BSM physics. Okay, now axions have numerous natural production mechanisms in the early universe. And the one that we'll be focusing on today is the misalignment mechanism. So in order to make our discussion of misalignment a little bit simpler, we can replace the axion field phi with theta, which is just the axion field over its decay constant. This makes the potential 2 pi periodic. And note out front, I've replaced the instanton scale with the axion mass squared times the decay constant squared. Okay. Now, the usual story of misalignment goes as follows. During inflation, supposing inflation takes below the decay constant, the universe is expanding exponentially quickly, and the axion field is stretched and flattened so that everywhere in the universe, it's exponentially flat. This means that we can replace the axion field with its spatial average, capital theta, and we'll be working in capital theta for the next several slides, basically. Now, this capital theta, this initial homogeneous expectation value, can be anywhere in the interval minus pi to pi with roughly equal probability. This leads to the expectation that the initial energy density of the axion field is on the order of the instanton scale, okay, m squared f squared. Now, this initial energy density doesn't stick around forever. Eventually, it begins diluting due to the expansion of the universe. And we can understand this dilution by looking at the equation of motion for the homogeneous mode, capital theta. And this equation should look familiar from classical mechanics. This is just the equation for a damped pendulum. The only real qualitative difference between this setup and what you might find in an undergraduate lab is that this damping term is the Hubble parameter, which is a function of time. So at very early times, the Hubble parameter is really, really big, and this holds the axion at its initial condition. Only once the Hubble parameter dilutes and the universe expands, slowing the expansion of the universe, can the axion begin oscillating. And this happens exactly when the Hubble parameter drops below the axion mass. And we can see this happening in the plot on the right. And after only a few oscillations, the axion's damped down to the bottom of its potential, where we can approximate sine theta as theta. And at this point, it's just the dynamics of a classical harmonic oscillator. And we know how the energy density of the harmonic oscillator dilutes in an expanding universe. It scales like 1 over volume, or like cold matter, which during radiation domination scales like t to the minus 3/2. Okay, so this is the usual misalignment story. And now I'm going to switch gears a bit and introduce the Axiverse. Okay, So string theory, in order to be mathematically consistent, must take place in 10 dimensions of space-time. However, as I think we're all familiar, we live in 4 dimensions of space-time. And so the other 6 dimensions, if they exist, must be wrapped up quite tight so that we have not already observed them. And in going from the 10-dimensional string theory down to our 4-dimensional effective theory, we introduce a bunch of axion-like particles corresponding to the topologically distinct ways of winding around these compactified extra dimensions. Now, this 6-dimensional manifold, in general, can be quite topologically rich. And this leads to the prediction of numerous axion-like particles. In the specific examples that I'm aware of, they can be on the order of hundreds. Okay. This prediction is known as the Axiverse. Now, in the Axiverse, we often think of each of the axions as living in a single cosine potential. Here out front, the instanton scale is now given by the UV scale or the string scale or the Planck scale, exponentially suppressed by this quantity S, which is the string instanton action. If S is on the order of hundreds, then the axion can be a naturally ultralight particle. Now, each of these axions, each of these Axiverse axions, lives in the cosine potential that we looked at on the previous slide, and thus it can be produced exactly in the same way by the misalignment mechanism. This means that we expect the final energy density of those axions being produced by the misalignment mechanism to scale like the axion mass to the 1/2 power times the decay constant squared. Okay, so this is kind of the vanilla expectation. And in this talk, I'm going to address the following 2 questions. When does the assumption that the axions evolve independently in their own individual cosine potentials break down? And what are the consequences of this breakdown? Okay. So why might we expect such a break to occur? Well, generically, when you have a theory of n axions, they will couple to one another through m instantons. Each axion phi j with its own decay constant fj talks to every other axion in the theory through this charge matrix qij. Each instanton scale has its own constant phase offset delta I, and the instanton scales are all exponentially suppressed relative to the UV scale by their own string instanton actions. Okay. Now, in the absence of other priors, we might expect that these string instanton actions are uniformly distributed over some interval. This leads to the prediction that the instanton scales will be log uniformly distributed. And this roughly corresponds to the statement that the axion masses will be log uniformly distributed. So for example, if you have 100 axions. Yeah.
Mm-hmm. So sorry, maybe I missed something, but so these axions are some angular variables.
Mm-hmm. Mm-hmm.
And is it clear that they are all correspond to circles?
Yes. So these are like yes, they correspond to the winding of like a 4-cycle around. I'm not a string theorist, so I'm not going to be able to put it in their parlance, but yeah, they correspond to basically winding around some manifold.
But the manifold is a torus, or could it also be?
Yes, it's compact. It's compact. So these 6 extra dimensions are compact manifold. Yeah.
No, I'm not just asking about compactness, but
oh, sorry. I mean, it is a torus. Yes, they're periodic. Yeah.
They can't be spheres, like 2 spheres.
They have to be, I think, geometrically flat, right? So I don't think, I need to think about that, whether you could have something like a sphere. These are Calabi-Yau manifolds that people think about for the most part, which are geometrically flat.
Yeah, I see. Okay.
Yeah. Sorry if that's not a complete answer. But yes, they're spatially flat, and I think this requires that they're like a torus. But yeah, I'm not certain. This is a good question.
Okay.
Okay.
All right.
Good. So, right. So in the absence of other priors, we might expect that these string instanton actions live in some uniform, are distributed over some uniform interval, which leads to the expectation that the string instanton scales are log uniformly distributed. And this leads to the prediction that the axion masses are log uniformly distributed. So if you say have 100 axions whose masses are distributed over 100 orders of magnitude, on average, you expect each axion to be 1 order of magnitude away from its nearest neighbor. However, due to fluctuations in the S's, some axions will have masses that are further apart, and some axions will have masses that are closer together. And it is the axions that have masses that are closer together that will be the subject of the rest of this talk. And we call those friendly axions.
David,
So why are we, yeah.
Why do you take 100 orders of magnitude as being this span over which the axions are like?
I mean, this is a highly model dependent claim. You can have much bigger distributions. You can have smaller. It depends on like the volume of the extra dimensions, which if it's really big, you get bigger, you span more orders of magnitude. You're exponentially suppressed by the volume of the extra dimensions, which enters in the string instanton actions. So in other words, if you have a really large volume compactification, you'll end up with axions whose masses span like thousands of orders of magnitude, and then maybe you won't expect friendly pairs to emerge.
And so like what kind of extra dimension scale would correspond to 100 orders of magnitude, let's say, just as like the base?
Yeah, it's okay. I don't have the numbers off the top of my head. Yeah, in the examples I'm aware of, you do end up with mass coincidences within a factor of order 1. But the distribution is not really uniform. Like it's close to it. It's quite complicated. I think Liam McAllister's group in Cornell has spent a long time looking at these distributions of instanton scales, and some of their papers have more precise answers to these questions.
Gotcha. So 100 orders of magnitude is somehow a vague ballpark of what people come up with using.
I mean,
like,
the thing is,
out by LHC or something.
Yeah, so 100 orders of magnitude, I just take because it's an easy, like, we think there are probably 100 axions if in these kind of generic scenarios, but 100 orders of magnitude, that's really, I don't have any particular reason for choosing that number. It's kind of not too big, not too small. There's no physical reason I picked that. However, the particular compactification.
You take the largest extra dimension that's compatible with LHC. Do you know what that would then come out to be?
No, probably the distribution would be way too small. I don't actually, I don't know these numbers. Yeah. Right. So, the particular examples that people have studied fairly extensively are fairly specific. These are like type 2b compactifications, and they usually study like very specific points on like what's called the Kähler cone, like, either towards the tip of the Kähler cone or, somewhere near there. And all of these choices, impact the distribution of instanton scales. And, really I'm trying to take a model independent stand here. Just, there's this generic expectation that the instanton scales are exponentially suppressed by a scale. And these are kind of the natural objects that are kind of order 1 distributed. And so you would expect logarithmically distributed masses. And so, I'm not really trying to say that there is a particular model that I'm aware of that generates this picture. It's more, this is kind of a generic expectation. What kinds of distributions give rise to this interesting stuff that I'm about to talk about? Yeah, so yeah, sorry if that's not entirely satisfactory. Yeah. Okay. Right. So yeah, with that said, this is a generic expectation. I'm really trying to take the standpoint that that this is something that you can ask, does your model have this in it? Not that there is a particular model that I have in mind where this happens. Okay, that's kind of the standpoint I'm trying to take. Okay, so why are we interested in friendly axions? So friendly axions are axions whose masses are nearby one another. It is these axions for which the assumption that they evolve independently will break down. This is because friendly axions have similar masses and thus similar dynamical timescales. And when you have similar dynamical timescales, the axions coupled through this joint nonlinear potential can dynamically resonate with one another or synchronize. This means that their timescales can dynamically shift towards one another because of the nonlinearities in the potential. And when you have dynamical resonance, this leads to efficient energy transfer between the axions and thus enhanced observational prospects. Okay, so that's really the key takeaway from this talk. The assumption that axions evolve independently breaks down when you have friendship, and this leads to enhanced signatures. Okay. And there's the additional point that I'll make at the end, that if you observe an axion that couples surprisingly strongly to your experiment, then it can tell you where to look to find its friend. And then you can discover multiple axions in this way, or at least reject the mechanism. Okay. So I've given a little bit of background and motivation for why we might want to think about friendly axions. And then the rest of the talk, I'm going to address their dynamics and their signatures. And roughly what we'll see is that the dynamics of the axions when they're spatially flat, meaning homogeneous, will roughly correspond to enhanced direct detection signatures, while the growth of density perturbations will roughly correspond to enhanced gravitational signatures. But in fact, if the density perturbations grow too fast, then these density perturbations can actually back-react on the homogeneous dynamics and modify the direct detection signatures. Okay, so I'll get into all of this. And to begin, unless there are any more questions, I'll begin by discussing the homogeneous dynamics of friendly axions. Okay. So the huge multi-axion, multi-instanton potential that I wrote down in the introduction is far too complicated to analyze by hand. So instead, we'll focus on the following two-axion, two-instanton potential. The axions phi s and phi l, I will call the short and long axion respectively. Short and long refer to the relative size of their respective decay constants, the short axion having a smaller decay constant than the long axion. The short and long axions couple to one another through this first instanton lambda 1, while the long axion receives its own instanton contribution lambda 2. In order to make our discussion a little bit simpler, we can work in terms of the angular variables theta s and theta l, which are just the axion fields divided by their respective decay constants. And I can pull out an overall factor of lambda 1, which I've rewritten in terms of the short axion mass and decay constant, m and f, respectively. And what's left over is the relative size of lambda 2, which I've written in terms of mu and f, the ratio of the long to short masses and the long to short decay constants, respectively. Now, as I mentioned, we'll want to think of the short axion as having a smaller decay constant than the long axion. This, yeah. Oh, did somebody have a question? Okay. We'll want to think of the short axion as having a smaller decay constant than the long axion. This did not need to be the case. In fact, it could be the other way around. But in order to have interesting dynamics, you'll want the long axion to have a decay constant bigger than the short axion by at least a factor of 3. It could be much, much, much bigger, but 3 is roughly the threshold for interesting observational signatures. Okay, so again, I'm taking kind of a model-independent standpoint. Yes, we did pick a particular model. There are reasons that this kind of model is, what you might expect. But I'm not trying to motivate the choice of f being bigger than 3 by any particular UV theory. Okay. On the other hand, the mass ratio should live in some order 1 interval. Okay. This is the condition of friendliness. So this is what having this distribution of axion masses buys you. if your distribution is not too broad, then you will have mass coincidences. And this is what will lead to interesting nonlinear dynamics. Okay. And in this particular potential that we've chosen, the mass ratio needs to be smaller than 1, but not too far from 1. Okay, this basically says that the long axion needs a smaller mass than the short axion. It could, in fact, have been the other way around. This depends on the particular form of the potential. So this particular window is model dependent, but the fact that mu has to be within some order 1 interval is not. That's the condition of friendliness, and that's generic. Okay. So before I get into the dynamics of this coupled axion model, I think it's first helpful to look at what happens for uncoupled axions. So here I've written down the same model, but I've simply removed the long axion from the mixing instanton lambda 1. Or not lambda 1 anymore, it's m squared f squared. And we already know what happens in this potential. If both axions start out with order 1 initial misalignment, then the initial energy densities of each axion will be given by their respective instanton scales. And the long axion's instanton is enhanced by this factor of f squared. So the long axion will dominate the initial energy density ratio by a factor of, f squared. Now, because both axions have similar masses, mu is order 1, their energy densities begin diluting like cold matter at roughly the same time. This means that the initial energy density ratio is preserved through time. Okay, so the final energy density ratio is the same as the initial energy density ratio. The short axion is down by a factor of f squared. Okay. So we can see this by looking at a plot of the energy densities versus time. And what we see is that there is this initial energy density hierarchy, which is on the order of f squared. The energy densities begin diluting like cold matter at roughly the same time. And the final energy density hierarchy is the same as the initial energy density hierarchy. Okay. So now what happens when we introduce, or I should have mentioned, this is the long axion, of course, and this is a short axion. Okay. So now what happens when we introduce the long axion to the mixing instanton, going back to our coupled model? Well, importantly, the short axion energy density will change its evolution dramatically, and it will be in response to a very simple change to the short axion equation of motion. So let's see how that happens. Okay, so the short axion energy density, instead of diluting right away like cold matter, instead stays at a constant energy density. Okay, what's going on there? Well, this change is in response to a very simple change to the equation of motion. Now the long axion is showing up as an external driver of the short axion. This external driving, naively, in the case that we had thought that the short axion was, say, a linear oscillator, would do nothing, right? The long axion has a mass that's different than the short axion's mass by order 1. And so you would not expect any significant energy transfer between these non-resonant axions. But we know that the short axion lives in a potential that's just like a classical pendulum. And we know that a classical pendulum has a frequency that depends on its amplitude. In particular, the frequency of a pendulum can be anywhere between its rest mass and 0, okay, when it's in its unstable equilibrium. Which means that there is a particular short amplitude or short axion amplitude that will give the short axion a frequency that matches the long axion. And the tendency for the short axion to align itself by adjusting its amplitude so that its frequency matches that of the long axion is called autoresonance. And it is this process of autoresonance that I'll spend the next several slides discussing. And the real important consequence of autoresonance is that the long axion transfers a large amount of its energy density to the short axion. And this energy density transfer will be what is responsible for enhancing direct detection signatures of the short axion. Okay. In fact, in this particular example, the short axion ends up dominating parametrically like a factor of f squared, which is exactly the opposite of the initial energy density hierarchy. Okay. nonlinear effects will change this result, or sorry, spatial fluctuations will change this result, but really you get a huge amount of the energy density coming from the long axion to the short axion. Okay. Any questions about this picture before I move on? Okay. So on the next several slides, I'll address the following two questions. What are the dynamics of autoresonance? And how friendly do axions need to be for autoresonance to be common? In other words, how close do their masses need to be? So to begin, I'll address the first question. And when you want to study the dynamics of a damped driven oscillator, the first place to look is the resonance curve.
So can
So
I just
here,
ask? So this was, you're dealing with just two, but in general, if you have a whole spectrum, then would you expect some sort of Boltzmann distribution of energies, or?
is good. So this is a good question. You know, what I think it's a very hard question. In this particular two axion example, you know, I think you would have expected perhaps that the energies of the two axions would be equipartitioned, right? In fact, that's not what we observed. We observed kind of energy density transfer favoring the short axion. And this seems to me to be very non-thermal. But it's a good question. If you have, you know, large numbers of axions, all with similar masses, what happens? It's hard to say. This is a good question. And we have not addressed that. Yeah.
Can I ask a question in response? How frequent is it that you would have more than two that would be kind of in the same mass range?
So again, this is, you know, if you have like say 500 axions distributed over, you know, 100 orders of magnitude in mass, then fairly frequently. But if you have, you know, 100 axions distributed over 1,000 orders of magnitude, then it becomes less frequent. So, you know, this is the particular physics that we're looking at here is kind of in the sweet spot where you expect coincidences between some axions, but rarely between some pairs of axions, but rarely between triplets and quartets and so on. But yeah, I mean, it's an interesting question, and you know, we expect some interesting stuff to happen there, but we have not actually worked out the physics. Yeah. Thank you. Yeah, the two axion example is definitely the simplest to work out by hand. Once you, I mean, it's probably, you know, once you get into a three-body problem, things famously become more complicated. So, okay, so unless there are more questions, I'll discuss the dynamics. Okay, so when you want to understand the dynamics of a damped driven pendulum, the first place to look is the resonance curve. Okay, so this plots the equilibrium amplitude of the short axion versus the relative driving frequency of the long axion. Okay, the long axion relative driving frequency is just the mass ratio, mu. Okay. Now, the short axion equation of motion, unfortunately, has time-dependent coefficients. The Hubble damping scales like 1/t, while the long axion amplitude scales like t to the -3/4. Okay, so there is no real sense in which you have an equilibrium damped driven oscillator. But thankfully, if t is bigger than 1 in these units, these coefficients evolve slowly compared to the time scale of the short axion oscillation. And this allows us to take the adiabatic approximation, where we instantaneously fix these coefficients and compute the equilibrium of the short axion amplitude. Okay. So in this equilibrium, in this adiabatic approximation, we can plot the resonance curve. And first, let's discuss what happens when you ignore the nonlinearity in the potential. In this case, the short axion is just a damped driven oscillator, or harmonic oscillator. And we know exactly what happens there. It has the maximum response when it's driven exactly on resonance. Okay. So this is just exactly what you would have expected. Only when the axion's masses are exactly matched do you get a large response. On the other hand, if the short axion, if we now include the nonlinearity in the short axion potential, it now lives in a potential that's just like a classical pendulum. And at large amplitudes, the pendulum frequency shifts towards smaller frequencies. Okay, this causes the resonance curve to bend to the left. This opens up the possibility of having up to 3 equilibrium amplitudes at a given driving frequency. In other words, we have this small amplitude equilibrium, which we call a linear resonance because it's really close to this blue curve. Up here, we have 2 nonlinear resonances. These have no analogy to the harmonic oscillator resonance curve. And this lower resonance is unstable. We don't care about it. You'll never get there. But this upper resonance is stable. And it's this upper resonance that represents where the short axion is held during autoresonance. This is where it was when its energy density was constant. So then the question is, how do you get to this nonlinear resonance that seems like a kind of hard place to get to, especially given that there's this equilibrium down here, from generic initial conditions? Why should you end up here? And that's what I'll address over the next couple of slides. Are there any questions about this picture before I move on? Okay. So now that we've seen a particular instant in time, what the resonance curve looks like, we can now look at a sequence of resonance curves as we slowly vary these coefficients. Okay. And what we'll see is that the resonance curve evolves in a way that lifts the axion up to the nonlinear resonance if it's driven at a frequency that's not too far from 1. On the other hand, if the frequency is fairly detuned from 1, the axion will be dropped down. Okay. So let's see how this happens. Okay, so these white dots, again, represent 2 particular driving frequencies and the short axion equilibrium amplitude. And what we see is that this axion got lifted up, while this one got dropped down. Okay, so why did that happen? Well, this is all because the Hubble damping falls off faster than the long axion amplitude. Okay, in other words, at early times, the damping is large, which flattens out the resonance curve. But at late times, the resonance curve is sharply peaked because the damping is negligible compared to the driving. And the evolution between these 2, the initial and the final resonance curve, lifts the axion up to this nonlinear resonance. Okay, so that's what's going on for autoresonance. That's why generic initial conditions, assuming your driving frequency is not too far from 1, gets lifted up to the nonlinear resonance. So where is this threshold where you get lifted up and where you get dropped? Well, we can see this by looking at the same video and pausing at a particular instance. When the resonance curve becomes vertical, we see that any point to the left will not get lifted up and any point to the right will. The exact location of this threshold depends on things like the initial amplitude of the long axion. In particular, if the initial amplitude of the long axion is close to 0, then this threshold shifts to the right. Larger initial amplitudes shift it to the left. Okay, but the point is that order 1 different masses can resonate dynamically because of this process. Okay. So with that said, I've addressed the dynamics of autoresonance. They're just the quasi-equilibrium dynamics of a damped-driven pendulum. Crucially, the damping falls off faster than the driving, which is a scenario that naturally emerges in the cosmology of scalar fields. Okay. So that's autoresonance. And now over the next several slides, I'll try to address the question, how friendly do axions need to be for autoresonance to be common? How close do their masses need to be? And the first place to look when addressing this question is this plot here, which at first glance looks a little bit complicated, but it's actually quite simple. So what we're plotting here is the final energy density ratio of the long to short axions versus the initial misalignment, okay? The short axion and the long axion, initial misalignments. Now, the darker regions correspond to the short axion dominating, while the lighter regions correspond to the long axion dominating. Okay, so what's going on here? Well, I think it's helpful to first look at what happens if the long and short axions are uncoupled. Okay, this is the same uncoupled model that we looked at in the beginning. What happens here? Well, we know that the long axion, if both axions have order 1 initial misalignment, will dominate. Okay, and that's what these white regions correspond to. There's only this narrow black region where the short axion dominates. And the reason it's dominating there is that the long axion has basically 0 initial misalignment. Okay, the long axion is starting with 0 energy density, so of course the short axion dominates there. So when we look back at this plot, we see that this inner band is entirely trivial. This is not an interesting part of the plot. What is interesting is these dark regions up here, where in the uncoupled model, we would have expected the long axion to dominate, but instead the short axion dominates. And these bands, in fact, exactly correspond to autoresonance. And the important takeaway from this plot is that these white regions and these gray regions take up roughly the same amount of parameter space, okay? At mu equals 0.85, half of your initial conditions autoresonate and half of them don't. But now what happens if we want to understand the fraction of autoresonant parameter space as a function of mu? Well, to understand that, we can look at the following plot. It looks a little complicated, but again, I assure you it's quite simple. So on the vertical axis, we're plotting the ratio of the short to long final energy density ratios, measured again at some late time after energy density transfer is stopped. And on the horizontal axis, we're plotting the mass ratio. Each vertical strip of this plot should be thought of as a histogram over the space of initial conditions of the long and short axions. In other words, we take this plot at a particular mu, and we count the number of pixels in this plot that correspond to a final energy density ratio. And we color this plot darker at that particular final energy density ratio. So in this range between mu equals 0.5 and 0.75, we see that the long axion dominates by roughly a factor of f squared. Between mu of 1 and 1.5, the long axion again dominates by roughly a factor of f squared. Of course, as you go towards mu equals 1, you get linear resonance, and thus equipartition will occur. And were these axions only linearly coupled, we would have expected the long axion to dominate in this strip here as well. But in fact, that's not what we see. What we see instead is that the short axion dominates by exactly the amount we would have expected the long axion to dominate by a factor of f squared. So to understand the fraction of initial conditions that end up autoresonating, all we have to do is add up the points above the horizontal axis at a particular mu. And we do that in this inset plot here. Okay. And what we see is that between mu of 0.75 and 1, between 75% and 25% of initial conditions end up autoresonating. And this is what we'll take as our kind of fiducial range for autoresonance. Roughly, you need masses within 25% of one another to get half of all initial conditions to autoresonate. Okay, so this is the autoresonance band. Now, in principle, it actually can be a little bit larger. There's this tail that we're not accounting for. But as you get towards the end of this tail, you need exponentially fine-tuned initial conditions in order to get autoresonance. So we simply discount it. Okay, so with that said, I've addressed how friendly axions need to be for autoresonance to be common. Roughly, you need to be in this 25% mass window. The theoretical range is somewhat larger, but when you get down towards this theoretical minimum, you really need fine-tuned initial conditions to get autoresonance. And so, we'll not worry too much about those initial conditions. Okay. So any questions about the dynamics of the homogeneous modes before I move on to density perturbations? Okay. So now I'll briefly discuss density perturbations. So during autoresonance, the short axion is held at large amplitudes where attractive self-interactions are strong. This is what is responsible for reducing the fundamental frequency of the short axion below its rest mass, okay, the attractive self-interactions. But of course, attractive self-interactions don't just reduce the fundamental frequency, they're attractive. They want the short axion to clump up, okay? So if you have some spectrum of initial perturbations on the short axion, say from inflation, like the adiabatic spectrum of perturbations coming from inflation, then the short axion will cause these perturbations to grow. In particular, it is horizon-sized modes at roughly the time the axion starts oscillating that get produced the most. And these modes then collapse early during matter domination into dense galactic substructure. And we can search for these dense substructures using astrometric and photometric searches. And I'll get into that at the very end. But before I discuss signatures, I want to briefly discuss how large fluctuations that form during autoresonance, non-perturbative fluctuations, where we can't neglect the spatial variation in the axion field anymore, can actually modify our conclusions about the homogeneous evolution of the axion. So here I'm plotting the fluctuations in the short axion energy density over the average short axion energy density. And what we'll see is that very rapidly, these perturbations kind of, explode out of nowhere and coalesce into these spherical objects called oscillons. Okay, these oscillons are examples of non-topological solitons. Their decay is not prevented by any conserved number. And the formation of these oscillons is actually is really important to the evolution of the energy densities of the long and short axions. When the oscillons form, they can either disrupt autoresonance if they form during autoresonance, or they can actually transfer energy from the short axion back to the long axion if the oscillons form after autoresonance. So to see this happening, we can plot the energy density of the long and short axions. Again, long axions up here, short axions here, versus time. The blue and pink curves correspond to the energy densities averaged over the box of a 3+1D simulation of friendly axions, while the white and beige curves correspond to our homogeneous prediction from the previous section. And what we see is that when oscillons form, if they form during autoresonance, the short axion gets disrupted. Its autoresonance stops, and the energy densities of the long and short axion begin diluting like cold matter at that point. And the energy density ratio is then frozen. Okay, so there's energy density transfer here, 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 up until the point of oscillon nucleation, and then the energy density ratio is frozen. And this roughly corresponds to an upper bound on the amount of energy transfer you can get. Roughly, the short axion energy density can be enhanced by a factor of 30 squared, which corresponds to the point at which oscillons will start to form during autoresonance. And any larger decay constant ratios, say f of 50, f of 100, will transfer no more energy to the short axion. You get cut off at about a factor of 1,000. Okay. So as I just mentioned, if the decay constant ratio is bigger than about 30, oscillons nucleate during autoresonance, disrupting the autoresonance. But what if oscillons nucleate after autoresonance? This happens for decay constant ratios between about 7 and 30. And we see in these plots the 3+1D simulation versus the homogeneous expectation. And we see them matching extremely well at early times, here, here, and here. But suddenly, at a particular point, they diverge from the homogeneous expectation. So what's happening there? Well, the short axion oscillons nucleate at this point. And when the oscillons form, they actually efficiently transfer energy between the long and short axions, roughly leading to equipartition in the volume that forms oscillons. Okay, so in this range of parameter space, we expect the long and short axions to be roughly co-dominant. Okay, and this is important for direct detection signatures. Okay, so with all that said, now I'll get into the direct detection signatures of friendly axions. And to kind of start off, I'll briefly remind us how we look for cosmologically produced axions. So typically when we're looking for axions, in particular their axion-photon coupling, we build a cold box, fill it with a strong magnetic field, wait for an axion to come in, scatter off of that magnetic field, and produce an outgoing photon. The flux of outgoing photons is proportional to the axion-photon coupling squared times the ambient axion energy density. So this figure, GA gamma gamma squared rho, is kind of the figure of merit when it comes to axion direct detection. So for a moment, consider a single axion living in a single cosine potential, a lonely axion. We know how its relic abundance scales. It scales like the decay constant squared. On the other hand, the axion-photon coupling is expected to scale like 1 over the decay constant. Okay. So this figure of merit, GA gamma gamma squared rho, is independent of the axion-photon, or sorry, is independent of the decay constant. What this means is that if you have an axion with a tiny decay constant that only comprises a small subfraction of the dark matter, small subcomponent of the dark matter, it will be exactly as visible as an axion with the same mass, but a much larger decay constant that comprises all of the dark matter. In other words, dark matter haloscopes are not sensitive to the fraction of the dark matter that the axion composes if that axion is undergoing misalignment production. Okay, so we can now plot our direct detection prospects in terms of this GA gamma gamma root rho, this figure of merit versus the axion mass, and we'll get signal strengths for axions produced with an initial misalignment that don't depend on the decay constant. Okay, so an axion of a particular mass with an 0.1 pi initial misalignment will produce a signal strength in your detector that looks like this, independent of its decay constant. 0.5 pi and 0.999 pi. The reason I put 0.999 pi here is because really this represents kind of a soft upper bound on what you could expect the signal strength of vanilla misalignment axions to produce. To get signal strengths that go well beyond here, you really need exponentially fine-tuned initial conditions to the top of the potential, and this is exponentially unlikely. And only if you have exponentially fine-tuned initial conditions will you get order 1 improvement in the sensitivity. Okay, so this is kind of the picture of vanilla direct detection of an axion-like particle produced via misalignment. So imagine we were living in an Axiverse, that's perhaps densely populated, meaning that there are, perhaps a few axions per decade in mass. Then if all the axions are just uncoupled, produced in this standard way, then as I build my experiment, I won't see anything as I build better and better experiments until I get down into this window, at which point I might detect a few axions, for example. Okay, so this is kind of the usual expectation. Okay. Now what happens when we have friendly axions? Well, the long axion transfers some large fraction of its energy density to the short axion. So the short axion has an energy density that's enhanced by a factor of roughly the decay constant ratio relative to the lonely expectation. In other words, the short axion has a small decay constant, but it has the energy density of an axion with a much larger decay constant. You get the best of both worlds. You get the strong coupling of the small decay constant, and you get the more axions coming from the larger decay constant. This means that you get enhanced direct detection prospects And importantly, these enhanced prospects are independent of whether the friendly pair is all of the dark matter or a small subcomponent, okay? So if you have a friendly pair in your theory, you will get enhanced direct detection prospects. So on our direct detection parameter space, I've plotted kind of the upper bound of what you would expect the signal strength of friendly axions to be. Remember that above a decay constant ratio of about 30, you don't get any more energy transfer because of the from the long axion to the short axion, because the short axion forms non-perturbative structures that knock it off of its autoresonance. So as you increase the decay constant ratio, you go up, up, up in signal strength until you hit this wall, and then you get stuck there. But what does this mean for our direct detection experiment? Well, as I'm building better and better models of my experiment, eventually I'll enter this window, and perhaps I see something. Maybe I see something here, okay? Well, okay, this could be any number of things. It could be photophilic, it could be a photophilic axion, it could have had an anomalously fine-tuned initial misalignment, or any other number of mechanisms that lead to enhanced relic abundance of the short axion, or of an axion. But it could also be that it has a friend. And in the case that it has a friend, we know exactly where to look. It'll be down here. And then we can build a more targeted experiment to search for the friend and either confirm or reject the mechanism. Okay, so that's really the takeaway here. So friendly axions are highly visible. And if you see a highly visible axion in your experiment, then you should look hard at nearby masses to confirm the mechanism. You can build a resonant experiment to scan, an order 1 part of mass parameter space, for example. Also, I'll mention that, if you do have a friendly axion in the mass range of your experiment, this will be the first thing that you see. Okay, so if these exist, then they can provide a path towards discovering other axions. Okay, but what about gravitational detection signatures? In the previous section, I was very careful to emphasize that you don't need the friendly pair to be all of the dark matter. In fact, it can be an arbitrarily small subcomponent of the dark matter still be.
Can I interrupt
Yes.
quickly?
Yes.
So you say that, let's say we find an axion.
Yes.
And then we look close by.
Mm-hmm.
Let's say we don't find anything. How far should we be looking out to figure out?
I would say a factor of 2 in mass. Anything larger, and you really shouldn't have a friendship. I mean, then you really need this doesn't. You need fine-tuned initial conditions to get this resonant energy density transfer if the masses are too far detuned. So really, you should only be looking over like a factor of 2 in mass.
I see. And that would that rule out string theory if you didn't?
No, it's not. This is a detection scheme, not an exclusion scheme. So this is like if you're an optimist, you say, well, it could even be this good. I could discover one axion and it could tell me where to find others. Of course, if you don't see that, then you haven't rejected string theory. Okay, this is not ruling anything out. But if you do discover it, then you have to come up with either some way to get these axions masses to be close to one another. There's no reason the axion masses have to be near one another, right? The only reason the axion masses would have to be near one another is because there are so many of them that just by accident, some axions have masses that are near one another. So you would have to come up with some reason axions have nearby masses. And this, I think, is hard to do unless you live in an Axiverse.
So I'm thinking, so are there particles that we know whose masses are close to each other? How about the U and D quarks? How much are
right. So I don't, they're fermions, and so I couldn't have this kind of dynamics. I mean, also they're strongly coupled, things are, and also they don't, yeah, I mean, you get kind of all sorts of messy things happening when you're coupled to the standard model. I don't think you would have misalignment happening with,
No, of course not, but I'm just wondering. Anyway,
But yeah, it
I
is a
know,
good question. You know, could you have this nonlinear energy transfer between standard model particles? I don't think so because they're thermalized. But perhaps I've not thought too hard about the situation.
Yeah. Okay. No problems.
Yeah, good. So yeah, any more questions?
Yeah, actually, one more.
Okay.
So, I mean, it could be that there are, I mean, there would be these global axionic strings, but I think you are sort of excluding them by only looking at misalignment.
Yeah, good. So there can be other mechanisms that produce some relic abundance of axions, right? So if you have, say, a pre-inflationary axion, you know, and maybe you have some, you know, some breaking of the global symmetry that gives rise to the axion, then you know, this might produce, I don't know, for example, domain walls that have a delayed decay, and thus you could get an enhanced relic abundance. You know, there's all sorts of mechanisms that enhance the relic abundance of axions. This is just one such mechanism that also points to where to find others. Okay, so you know, that's kind of the nice thing about this.
Okay.
Yeah. Sorry, I think did I address the original question you just had? I
It wasn't really a question. I mean, we know that the topology is there, but the strings may not be there because you can inflate them away. So
yeah, I think I don't personally understand this this topological defect formation for axions in the context of string theory. Okay, so I don't actually know how that happens there. I don't know, like, the analogy of, you know, Pechi-Quinn symmetry breaking. I don't know how that happens in string theory. You know, all I know is the low energy effective theory. So it's, I think even understanding a single axion is an interesting question.
nice.
Yeah.
Okay.
Good. So if, as I mentioned in the previous section, the enhanced direct detection prospects happen for even a tiny subcomponent of the dark matter. But gravitational signatures, in contrast, require the friendly pair to be all of the dark matter. Okay. This is because gravitational signatures require you to be a sizable fraction of the energy density of the universe. And so this only happens if you're all the dark matter. Okay, so just that's important to keep in mind. But if you are all of the dark matter, then the density perturbations formed during autoresonance collapse early during matter domination into dense galactic substructure. And we can look at the density of these substructure in what's called a halo spectrum. So the density of the substructure versus their mass. And in white here, we have the cold dark matter prediction. And in these multicolored curves, we have our prediction for various parameters. And what we see is that the density of the substructure is enhanced by several orders of magnitude, by 10 to the 3, 10 to the 6, 10 to the 4. And these extremely dense galactic substructures can be searched for using photometric and astrometric searches. And I want you to take away two key things from this plot. First is that the mass scale over which these gravitational probes are sensitive is roughly complementary to the mass scale over which the direct detection probes are sensitive. So it's roughly cut off here in the radio frequency band. And the second thing I want you to take away is that the decay constant ratio required to get these interesting signatures is not large. Okay, you only need a decay constant ratio of between 3 or 4 to get photometric microlensing signatures of critically lensed stars. Okay, so that's the key takeaway here. I can discuss this plot in more detail at the end. I'm just going to wrap up so people can leave. So to summarize, friendly axions are more visible than lonely axions. Discovering a highly visible axion should prompt a search for more weakly coupled axions at nearby masses. And if you discover a friendly pair in your theory, then this is evidence that we live in a dense Axiverse. Importantly, it's not if you don't discover this, it's if you don't discover this, it's not a proof that we don't live in an Axiverse. Okay. Okay. So with that said, thank you very much.
Thank you, David, for the nice talk. Any questions from the audience?
Yeah, I got a quick one. I hope it's quick. Back in the animation that you were showing us with the oscillons that form, they seem to form and then they hang out for a while and then they suddenly decay. Do you know anything about that decay rate or what that process is?
I do, in fact, have a paper on this. The decay rate is, so basically the way you can understand why an oscillon is long-lived is actually fairly straightforward. So the size of an oscillon has a frequency that's below the rest mass of the particle. So it's composed of states that are not on shell in the asymptotic space-time, or in the asymptotic, asymptotically far away. And the radius, the physical size of the oscillon, it goes like roughly 1 over the binding energy, okay? So 1 over the binding energy, or pi over the binding energy, sets the physical size of the oscillons. Now, the binding energy per particle scales like the square root. Let me write this out. Scales like, so the radius of the oscillon goes like pi over E bind, right? And the binding energy per particle scales like square root mass squared minus the frequency squared. Okay. So as the oscillon radiates away its binding energy, this quantity gets smaller and smaller. In other words, the radius gets bigger and bigger. And this now represents an object that's big and fuzzy, trying to produce semi-relativistic radiation. So for example, if you have a 3-to-1 process that's occurring, then the power radiated by the oscillon will scale exponentially. This is basically Riemann-Lebesgue, right? You have a big thing coupled to a small thing. It will scale exponentially like the wavelength of the or like the size of the oscillon over the wavelength of radiation. Okay. Now the wavelength of radiation is roughly some order 1 number times omega, right? Usually 3 omega if you have a 3-to-1 process. So in other words, this ratio gets bigger and bigger and bigger as the oscillon dies, exponentially suppressing its decay, making these long-lived objects, okay? But importantly, nothing stops their decay. Eventually they do die, and that's why they're long-lived, okay? So the oscillons are just big puffy objects, and so they take a long time to decay. Yeah.
And so the same thing that sets their size is setting their decay scale.
Basically, yeah. I mean, there's some details. Like they're very sensitive to the profile, right? There are some nuances that really do matter, but broadly speaking, it's that they're big, they decay slowly into relativistic modes. Yeah.
Okay. Thanks for the next talk. By the way, I have to run, but thank you.
Thank you for coming.
Any other questions for David? If no, let's thank David again.
Thank you, David.
Thank you.
Thank you.
Thanks, David.